the Dirac delta function. So think about the Heaviside step function. I've got a graph here. Again, yes, drawn in Microsoft Paint. The Heaviside step function is 0 until it reaches A, then it switches on, and then it's 1 afterwards. So it's 0, then it's 1. It's 0, boom, then it's 1. So what's the slope of this function? What's the derivative of this function? What's u prime, I guess? Well, the slope is easy over here. The slope is 0. The slope is easy over here. The slope is 0. The slope is 0 everywhere except for this one point where time equals a, where t equals a, where it jumps up. What's the rise over run? What's the slope here? It's a rise of 1 and a run of 0. 1 divided by 0, we can say that's infinity. So here's our Dirac delta function, our derivative of the Heaviside step function. It's 0 everywhere except for when t is equal to a, when it's infinity. So it's like an infinite spike. Now I guess another one of the things to worry about, well, we got a couple of things. What's this physically model? Well, if we're thinking about a spring problem, this physically models a situation where you don't apply a forcing function like a steady forcing function to the mass. You strike it with a hammer. It's like an impulse function. So the Dirac delta function will model a short, sharp shock hitting the weight with a hammer. So if we're going to be solving differential equations with the Dirac delta function, we're going to need to know what the Laplace transform of it is. So the first thing I need to do then is think about what's the integral from minus infinity to plus infinity of some function multiplied by the Dirac delta function. We're going to show that that's just equal to that function evaluated at the place where the infinite spike takes place. So there's a lot of different ways to do this. Probably the most elegant way, the neatest way, is to just do integration by parts. So I've got integration by parts on it here. The f is in the f spot. The g prime is in the Dirac delta function spot. Oh yeah, so if g prime is the Dirac delta function, then g, that's the Heaviside step function. So let's do this integration by parts. I need f times g, so f times, and the g is the f times g. The g is the Heaviside step function, so be careful of my diction here, but f times u minus the integral of the two things I made, and the two things I made then are going to be f prime and g, again the Heaviside step function, dt. And we're integrating from minus infinity to plus infinity. So using integration by parts, our integral then is equal to f times g, and again g is the Heaviside step function. We have to evaluate that at infinity minus evaluate that at minus infinity. Yes, it's an improper integral, and we're just looking at this in a kind of a casual way. And let's do that now. Well, at infinity, the u is equal to 1. So this is just equal to f evaluated at infinity, the limit of that approaches infinity. So again, casual, we'll just write that as f at infinity, but we mean the limit. And u at infinity is just 1 because we're past a, so the Heaviside step function past the switch point is just equal to 1. Minus, when I sub in negative infinity, we've got f at negative infinity, but it's times by 0 because the Heaviside step function is turned off at negative infinity. So that's this part. Minus, let's do our integral here again. Before a, our Heaviside step function is 0, so I can start this at a. After t equal to a, the Heaviside step function is 1, and now I'm just integrating from a to infinity f prime. Well, integrating f prime just makes f. So here I've got f at infinity minus f sub in the top minus sub in the bottom, that's going to be another f at infinity limit minus a minus f at a. So whatever these f at infinity limits are, they cancel each other out, and I end up with, well, proving what we wanted to prove, that the integral from minus infinity to plus infinity of a function times the Dirac delta function is just equal to that function evaluated at the time at which the spike happens. Now, a couple of things that we can do with this. If I ask, what's the area underneath that infinite spike? Well, there's a couple of different answers we could think about. You could say, well, an infinite spike's like, if I think of it as an infinitely tall, infinitely skinny rectangle, length times width is the area, but it's, infinitely skinny, so the area is going to be 0 because the width is 0. Or you could argue it the other way around. You could say, well, length times height, or width times height for the rectangle, and the height's infinity, so the area must be infinity. But we can use this argument that we just derived and make the f function 1, and now we know that this should be the function evaluated at a, so we end up proving that the area underneath that infinite spike is equal to 1. You'll often see the Dirac delta function show up in probability because it is a probability distribution. It's always positive. The area underneath it is 1. All right. But the reason we really wanted this rule is so we can take the Laplace transform of the Dirac delta function. So I'm going to take the Laplace transform. I've got it in the definition. The Laplace transform of the Dirac delta function, integrate from 0 to infinity, e to the minus st times the Dirac delta function dt, just to evaluate that integral. Well, let's think about this for a second. My Laplace transform definition starts at 0, but I could safely change this to minus infinity, since from 0 all the way back to minus infinity, I'm assuming a is a positive number, the Dirac delta function is 0 anyway. So that's their definition. But it's safe, we're just adding 0 if I change that 0 to a negative infinity. Well, now I'm integrating from negative infinity to infinity a function times the Dirac delta function. I'm going to go back to the thing that we proved here, the property that we proved, and the f is the e to the minus st. That should just be equal to the function evaluated at a. That's the property that we proved. So make t equal to a, and I'm done. The Laplace transform of the Dirac delta function is e to the minus sa. So we can do things like, well, we can do easy things. Like if I ask what's the Laplace transform of the Dirac delta function at 2, the infinite spike happens at 2, well, that's going to be straightforward. That's just e to the minus 2s. Done. What we can also do then is we can take the inverse Laplace of a constant. So if I take the inverse Laplace of, let's say, I don't know, 7. Well, if I think of that 7 as, okay, if I write it as 7, if I check my chart, I don't have anything that I Laplace into a constant. But here I can write this as e to the minus 0s, since that's just 1. And now I can see that that's just going to be 7 times the Dirac delta function shifted to 7. to 0, the unshifted Dirac delta function. So it lets us unLaplace constants as well. Let's do some more examples of this thing being, showing up in a differential equation. Here's linear second order constant coefficient non-homogeneous differential equation. We've got two initial conditions, y naught is equal to 0 and y prime naught is equal to 0. We could think of this as a spring question since all the coefficients are positive. And if it's a spring question where all the coefficients are positive, then we're thinking about this as the mass is 2, the coefficient of friction is 1, the spring constant is 2, the forcing function is that Dirac delta function shifted over to 3. So it's like someone hit the object with a hammer, the mass with a hammer at t equal 3 seconds. The initial conditions are it's not moving, y prime equals 0. It's at equilibrium, y equals 0. So if we didn't do anything to it, and we don't until 3 seconds, it should just sit there. So I expect my solution, since I have friction, I expect my solution to be 0 until it gets hit, and then it should wave if I get complex conjugate eigenvalues, and the oscillation should die down to 0. To figure out, there will be no waving, of course, if our eigenvalues are real numbers instead of complex conjugate numbers. How do I know which they are? Let's get the auxiliary equation. Here's our auxiliary equation. We get the eigenvalues, lambda equals to -1/4 plus or minus root 15 over 4i. So complex conjugate eigenvalues, we know we're going to get the oscillation and it dies down because the real part of the eigenvalue is negative. We knew the real part of the eigenvalue was going to be negative because all the coefficients were positive. So that means we've got a homogeneous solution equal to, wait a minute, now I'm approaching this by getting the homogeneous solution, and then I was going to add the particular solution, which I guess we know two ways to get the particular solution: unknown coefficients and variation of parameters. We were thinking about doing this with, or we needed to do this with Laplace transforms because of the Dirac delta function, but I do want to think about the homogeneous equation, the easy way, the eigenvalue way, just to sort of guide my Laplace transforms. So I knew my homogeneous equation was going to be some constant e to the -1/4 t sine root 15 over 4t plus some constant e to the -1/4 t cos root 15 over 4t. So I'm just thinking about this as going to be part of the solution. Now let's do this with Laplace transforms. So all of this was just sort of providing me some foreshadowing, providing me some information of what's going to happen when we do the Laplace transform. So let's Laplace transform the whole equation. I'm going to get 2 times the Laplace transform of y prime prime is going to be s squared f minus, well, both initial constants are 0, so minus s y minus s, or minus y prime, it's -0, plus, now I need the Laplace transform of y prime, sf minus 0 again, and now the Laplace transform of 2y, is equal to, here's where we needed our Laplace transform of the Dirac delta function, which is going to be e to the -3s. What's our next step? Solve for f. When I solve for f, everything's multiplied by the e to the -3s. I know that's going to create, when I unLaplace, that's going to create a Heaviside step function. If the quadratic here in the denominator factored, then I should factor it and then do partial fractions and break it into 2 pieces. It doesn't factor, so I'm going to need to complete the square. So I factored a 2 out of the bottom, then I completed the square. And I can see this as a number over s squared shifted plus b squared, and the square root of 15 over 16 is that root 15 over 4. I start to see where these pieces would start to happen. Now I can I want to unlaplace this piece. So I need to first match this. I'm going to, on the top here, there is no s on the top, so I'm going to unlaplace this with a sign. So I wish on the, instead of a 1 here, I wish this was a root 15 over 4. So I'm going to put 1 there and 1 there to balance. Now this fits into a shifted, now I'm going to unlaplace. So y is equal to this piece unlaplaces to be Heaviside step function at 3. This is just a constant. Now what's in the square bracket? What's in the square bracket would normally unlaplace to be e to the minus, it would normally unlaplace to be this, the shifted piece, and then the sign. It's a shifted sign, where the b squared is the 15 over 16, so the square root of that is root 15 over 4. But the argument inside the Heaviside, inside the square bracket, has to match the argument of the Heaviside step function. So that's not a t there, it's a t minus 3. Now I'm done. Well, I mean, there's a little bit of tidying you could do here with that constant. We could simplify it, but I do get what I thought that I was going to get. Y before t equal 3 is 0, because this Heaviside step function would be 0 multiplied by everything. After t equal 3, this Heaviside step function is 1, so it's a decreasing exponential multiplied by the sine function. It's like the we think we're getting the it's a decreasing exponential times the sine function. We're getting the physical equation that we thought we were going to get. Let's do another example. This one's written as a word problem, as a spring question. The mass is 1, so it's 1 times y prime prime. The spring, with the spring constant, there's no friction, so just plus y. Oh, that's going to be the way it's written now. That's simple harmonic motion equals the mass is struck by a hammer after pi over 2 seconds. So we have that Dirac delta function at pi over 2 seconds. So here's our differential equation. Y prime prime plus y is equal to the Dirac delta function at pi over 2 seconds. Initial conditions. Well, let's see here. It's released from rest 1 meter above equilibrium. So y naught is equal to 1 and y prime naught is equal to 0. It's released from rest. Take the Laplace of both sides. It's going to be s squared f minus s y naught minus y prime naught plus the Laplace of y is equal to our Laplace of a Dirac delta function, e to the minus pi over 2s. Solve both sides for, or solve for f. So we solved for f. Now we can unlaplace both sides. S over, that's just straight cosine t, plus our e to the minus pi over 2s. That's going to be our, going to unlaplace to be Heaviside step function turned on at pi over 2 seconds. Now what's inside the square bracket would normally unlaplace to be sine. But I don't just write sine, I write sine shifted, so the argument has to match the argument of the Heaviside step function. So it's not just sine of t, it's sine of t minus pi over 2. So there's my solution. But I think we can do a little bit better. We can, because they want me to draw the solution here. Well, sine of t minus pi over 2. That's the sine function shifted over pi over 2. So I can write this as cos plus a Heaviside step function times minus cosine. Now let's think about what that means. Before t equals pi over 2, the u is equal to 0, the Heaviside step function is 0, so it's just cosine. After pi over 2 seconds, this Heaviside step function turns to 1, so if I want to, I can write this as a split function. We ended up stopping its motion dead. Here's the algebraic way of writing it. We still haven't drawn the solution. For me to draw the solution, I'm going to go to Microsoft Paint and draw this in a horribly, that's my axis. It should drop down, cos of pi over 2 is 0, and it should stop and then be 0 afterwards. Yeah, looks like a toddler with a head injury drew that. But anyway, that's the graph.